All right. Well, week 10. We are almost at the end here, and we have a really short week this week. So we have one class meeting, which is today, and then we meet next week 3 times, and we're done. So wrapping things up quickly. I want to talk about one more application of Hamilton paths, and then I want to talk about Dijkstra's algorithm, which is that last homework question. But any questions other than those?
Those were my questions, but I'll let you get to them.
Cool.
So a path is anything that doesn't travel the same edge twice?
A path is just anything that starts from one vertex, goes to another, starts from that vertex, goes to another, starts from that vertex. And just a plain old path, it can go back and forth over vertices, it can go in loops, that's all fine. A simple path goes over an edge only once. It doesn't go back on itself, basically.
Okay, thank you.
Yeah, you're welcome.
I think the only question I had was on number 4. I just want to make sure that I'm doing it correctly, which would be mapping. Is that just lists on one side ABC, the other side XYZ, and then map which one is...
Oh, is this the isomorphism
like,
question?
Yeah.
Yeah, so just say, A maps to this, B maps to that kind of thing.
Okay.
Yeah.
And is it okay to do like 2 columns and then lines to each one kind of deal?
That would be perfect.
Okay, great.
Yeah.
And then I guess one other question, just for circuits, right, was it would be one that starts at one spot and ends at that same spot, correct?
Correct. Yep.
Okay. All right. Excellent.
All right.
So my quick question, I just remembered one more. So for a Euler path, it would be a path that traverses every edge at least once. But for a circuit, Euler path would traverse every single vertice at least once. But a Euler circuit would travel every single vertice and then end on the one that started.
Yeah. Except that for Euler paths, they travel along edges, right? So an Euler path travels along each edge exactly once. A Hamilton path visits each vertex exactly once.
Ah, okay, thank you.
Yeah. So yeah, the kind of quintessential Euler path question is this one. And so can you draw the shape without lifting your pen? So you can start here and go like that. That means you've got an Euler path. And then an Euler circuit, you would have to start and end at the same spot. So, there's an Euler circuit. Assuming you had 4 vertices.
So a Hamiltonian path, if you have 3 edges hooked to it, then there's absolutely no way you can do... There would be no way there'd be a Hamiltonian path, right?
Well,
you have to go through that vertice twice.
Let's see. So, there's a Hamilton path through here, right? I can go like that. And I've hit each vertex without repetition.
Okay. Interesting. So you're not worried about the edges on that?
You're not worried about the edges. You're not required to visit every edge. You're only required to visit every vertex.
Okay, maybe I have to relook at number 7 then.
Okay. So just one interesting application of Hamilton paths, which ties into Engineering 250 actually, like a lot of this course does. See in question 5 in the homework, it's asking for the length of a path. Oh, so let me do length of a path. So if you have a graph like this, I don't know, some connection of these, and you want to find the length of a path. Suppose it's the number of edges you go across, right? And you count multiplicities. So let's say you start from A and you go to B and you go to C and D and go to E, right? A, B, C, D, E. Well, your path length would be 1, 2, 3, 4. If you start from A and you go B, C, D, B, C, D, B, C, D, and then to E, your path length is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the length of a path is just the number of edges that you traveled along. And if you travel an edge more than once, you count it more than once. All right, so Hamilton paths, interesting application area. So let me make a graph that's going to look kind of funny. I'm going to have 8 vertices in this graph, and I'm going to call these 0, 0, 0, 1, 0, 0, 1, 1, 0, 0, 1, 0. So I'm just giving them binary numbers for their values. 0, 0, 1, 1, 0, 1, 1, 1, 1, and 0, 1, 1. And I'm going to connect these vertices with some edges like this. Yeah, it's a cube, but it's a graph, right? It's 8 vertices and it should be 12 edges. But I've suspiciously labeled these vertices with 3-bit numbers. And the question now is there a Hamilton path? Or even better, a Hamilton circuit. So a path which starts at one point, say right here, and travels through all of the vertices and then comes back to the original vertex. And it hits every vertex, but it hits it only once. And there are a number of paths we can find that do this. So let me show you one. Let's come down here. And then let's go up here. And then let's go across. And then come down. And come across. And come down.
And this doesn't have to be a continuous path, right? It just has to be a path.
If it jumps around, it's not a path. You can't teleport.
No. Meaning, like, you don't have to do it. You don't have to do it twice. Like, say on the homework, if you found a path that ended at F, it doesn't have to go back somewhere else.
If you're just looking for a path, you're okay. If you're looking for a circuit, you have to end where you started.
Yeah. Okay.
And this one, we're actually going to find a circuit. But yeah, a path can start and end at different points. So here's a Hamilton path. It visits every vertex exactly once, and then it goes back to where it started. And so if we were to think of 3-bit numbers, right, we've got 8 vertices. They're each tagged with a different 3-bit numbers. These vertices represent all possible 3-bit numbers. The interesting thing about the way I've drawn this, right, I laid this out like coordinates. So this is X, and this is Y, and this is Z. And the way I've drawn this, when you move along an edge, you change exactly one dimension. For example, if you move in this direction, you're moving along the Z-axis, and so the Z, the 3rd bit, changes. If you move to the right, that's the X-axis, so the X bit changes. And so along this path, when you move from one vertex to another, only a single bit changes. And if we write down the vertices in the order that we get by following this Hamilton circuit, we get 0, 0, 0, 0, 0, 1, 0, 1, 1, 0, 1, 0. And then we cut over here to 1, 1, 0, 1, 1, 1, 1, 0, 1, 1, 0, 0, and then we go back to 0, 0, 0. And does anybody recognize this sequence?
With that 250, it has to do with the, I can't think of the name of it at the moment.
It's the K mapping.
K mapping, yeah.
Yeah, this was the K mapping order that we used, which was an example of a gray code.
Yeah.
So,
right.
So gray coding was this idea that, you know, if we're trying to count from 0 to 7, we can do it with you know, weighted positional notation. But we get this artifact where, for example, when we go from 3 to 4, all 3 bit values change. And if they don't change at the same time, it's possible we could go from 0, 1, 1 to 0, 1, 0 to 0, 0, 0 to 1, 0, 0. We might have these intermediate states that are not actually intentional states. And if we have a Mealy machine where the output is a function of inputs, for example, as well as state, it's possible that these intermediate values could change an output to the system. And it could change a memory somewhere, which would have a lasting effect. So if we do our coding like this, when we move from any one state to the next state, at most a single bit changes. So our state would be 1, 1, 1, 1, 1, 1, 1, 1, 1, and at some point it'll go to a 1, 0, 1. And it's not going to go to an intermediate state, and so it helps us deal with glitches in
There was
systems.
a term for that, wasn't there? I can't remember, like a runaway or something like that. Or I can't remember what the term for like a glitch, a specific glitch where it doesn't switch properly.
Oh yeah, yeah. There's hazards, and there's race conditions.
Yeah, I think that's what
Okay, yeah. So this is a race
Yeah.
condition, right? Is this 1 and this 1 going to change at the same time that this 0 changes, or is one of those going to happen first? And you know, if this first bit changes first, we might go from 0, 1, 1 to 1, 1, 1, and maybe that's a do not use state, right? Maybe we only have 6 states in our machine, and this state is undefined. And when we get here, it, you know, opens up the water outlet on the cooling tank for the reactor, you know, and that's a bad thing. So we can do more glitch-free design by using this gray code, and we can discover gray codes by following Hamilton circuits around, you know, a graph like this.
You mentioned hazard
Mm-hmm.
before race condition. What exactly would you define as like a hazard? Like just a condition you wouldn't want to be in?
So I think a hazard is a setup for a glitch. I don't teach hazards in 250, but I think it's a condition which, if other things happen, could lead to a glitch. Whereas the glitch is the actual misbehavior. So if you have a circuit where the order in which the inputs change could affect the output, that I think is called a hazard in the text. Oh, and someone understands now why it's called a race condition. Yeah, that's exactly why. So it's a race to see which one gets through the circuitry first. All right, so that's just another application of Hamilton's, and that ties into digital logic. All right, so last subject for graph theory is the topic of shortest paths. And shortest paths, we're usually thinking about weighted graphs. And let's say we wanted to travel from, you know, vertex A to vertex Z. And we can ask, what's the shortest way to do that? Where length is defined as the sum of the lengths or the weights of each edge along a path. And so, you know, we probably don't want to go down here because this is length 4. We probably want to come along here as a length of 2. And we're trying to get to z. Well, if we come down here, we can do a 1 and a 3. If we come down here, we're going to have to do a 1 and a 6. So we probably want to come down here as 1, and then come along here as 3. That's a path of length 6. And we can probably convince ourselves by, you know, holding fingers on paths and thinking about it, there's probably not a path shorter than 6. And so that's the shortest path from one point to another. And for a small graph that we can sort of, you know, eyeball and take into our brains in one viewing, we can usually figure out a shortest path. But trying to teach a computer how to do this, that's a different matter, because computers don't share their intuition with us, right? We can't ask a computer to just sort of figure out what the shortest path is. We need an algorithm, a series of steps. And there's different types of shortest path problems. The one we're going to talk about is a setup like this, where we have weights on each edge, and the weights are positive. So we're not allowed to have negative weights on this. And negative weights are weird, because if we had an edge here with a weight of -4, we can find a really short path, right? We can come down here for 4, and then do -4 brings us to 0, that brings us to 3, -4 is -1, plus 3 is 2, and each time we go around this, our total path length drops. And we can make our path length, you know, -1,000,000 if we want, and then come out 3 more to get to z. So it's a totally different problem with shortest paths when you have negative weights. But if we just deal with positive weights, there's a pretty straightforward algorithm. It's called Dijkstra's algorithm. I think I might have it spelled right. There's probably about a 60% chance I spelled it right. Maybe. Seems like you couldn't avoid a loop of some kind, right? So usually when we're looking for a shortest path and we have positive weights, loops will not help us. Because if we take a loop somewhere, let's say we get to this point and we take a loop, we're back to where we started, and we've just added to our total path length. So we'll want to avoid lengths unless there's negatives, and that's the thing that makes the negative case or the signed case trickier. All right, so let me make a sample graph. And this is pretty straightforward to code, and you'll definitely do this at a university, possibly multiple times. If you do any game development, you'll do a lot of path finding, and you know, when you have someone chasing you, you can use Dijkstra's algorithm to let them figure out the most efficient way to reach you. And maybe when you're making a map, you'll find the most efficient paths from point A to point B, and you'll put some obstacles in those pathways and force the player to choose, do I want to take a quick path that's dangerous or a longer path that's safer? Yeah, so you'll definitely use some kind of looping in this algorithm. All right, so let me give you a high-level view of Dijkstra first, and then we'll actually go through this. So basically, you're trying to get from you're trying to find shortest path from some source node to some destination node. And we're trying to find a shortest path, because the shortest path may not be unique. If there's 2 or more paths of the same length that are the shortest, this algorithm may give you one, it may give you the other. It depends how you actually code it. but we're looking for a path with the shortest length from source to destination. And I'm going to suppose that for this example, we're starting from node A and we're trying to get to node Z. And we've got the weights on here, right? So we have positive weights. I think you can have weights of 0 also, and that's okay, just not negative. All right, so the algorithm is a pair of steps that we alternate. And the steps are basically the following. We do what's called visiting a node, and then we relax adjacent nodes. And it's this pair of steps over and over again. Visiting a node means saying, okay, we have found a shortest path to this node. It adds that to our final path solution. Relaxing adjacent nodes says, once I know how to reach this path, what's the best I can do to reach a neighboring path? Where a neighbor is an adjacent, so a vertex connected to the vertex we just visited. So node and vertex, I use those interchangeably. All right, so let's run through an example of this. Let's start with node A. All right, so I'm going to circle node A to say this is the node that I'm at, and my path to get here is basically, you know, just go to node A, and my distance to node A is 0. All right, oh, I forgot to seed the process. So there's a step 0, set initial distances. All right, so the node we're starting from, the distance to that node from the start is 0 because we're already there. But all the other nodes, the initial distance is infinity. So anytime you can write infinity as part of a solution, it's a good day. So the distance to B, C, D, E, and Z are initially infinity because we have not found a path to those nodes yet. All right, so we start off by visiting node A. We draw a circle around it to say we visited it, and we write down, you know, the path we took to get to that, which is A, comma, and the distance to A, which is just 0, because we're already there. Okay, now we relax adjacent nodes. Here's what this means. So far, you know, the distance to reach node C is infinity. But guess what? I've decided I can get to node A in a distance of 0, and I know there's an edge from A to C with a length of 2. Which means if I get myself to node A, and then I go 2 more, I can get to C. For a total distance of 0 plus 2 is 2. Well, 2 is better than infinity. So I'm going to record the following. I'm going to take out that infinity. I'm going to say, hey, if I go to node A and then node C, I can do that for a distance of 2. Okay, so I found a path from A to C. It may not be the shortest path. Similarly, from node A, there's an edge connecting me to B. Since the distance to A is 0 and the edge from A to B is 4, I can get to node B with a distance of 4. 4 is better than infinity, so I'm going to get rid of that infinity. I'm going to say, hey, if I go A and B, that's a distance of 4. Those are the only vertices connected to A. So that's the end of the relaxation step. Now we're going to go back and we're going to visit another node. Which node do we visit? The node that's closest to us that we haven't already visited. We can't visit A again because it's already circled. But there's 2 nodes that we know we can reach from A. There's node C and there's node B. This has a distance of 2, this has a distance of 4. All of these nodes, infinity, much bigger. So 2 is the closest node. We're going to visit this node. So I'm going to put a circle around it. And then we're going to relax all the nodes that are adjacent to C. All right, well, here's an edge of length 10. It takes me a distance of 2 to get to C. If I add 10, that's 12. I can get to node E with a distance of 12. That's better than infinity. So I'm going to change this to a 12. And the path to get here is to first get to C. So I'm going to go A, C, and then I'm going to go to E. From C, I also have an edge of length 8 going to node D. 2 plus 8 is 10, so I can get to this node in a distance of 10. That's better than infinity. So I'll say, okay, let's go to A and C and D, and that distance is 10. There's also an edge from C to B. It takes me a distance of 2 to get to C, and then if I go one more, that's a total distance of 3 to get here. 3 is better than 4. So I'm going to relax this node. I'm going to change the information about getting to this node. I'm going to cross these out, and I'm going to say, hey, if I go to this node first, which I do by going A, comma, C, and then I go from there to B, that'll be a distance of 2 to get to C plus 1. That's a distance of 3. And I'm done relaxing from node C. Go back to step 1, visit a node. Which node? The unvisited node that's closest to us. Well, here's a node of distance 3, 10, 12, and infinity. So our closest node is 3, so we're going to visit this node. Now we relax adjacent nodes. We're not going to relax this node. These nodes are visited. We don't relax visited nodes. We've already found a shortest path to A and C. So the only node that's connected to B is D. And 3 plus 5 is 8. That's better than 10. So we're going to relax this. We're going to change this path. The way we get here is come to node B. So A, C, B. And then from here go out to D. And the total distance will be the distance to B, which is 3 plus 5. That's 8. Alright, we've got vertices with distance 8, 12, and infinity. This is our closest one, so we visit D. We relax adjacent nodes. So 8 plus 2 is 10. That's even better than the 12 we had. So we'll relax that. Our path here is A, C, B, D, E, and 8 plus 2 is 10. And we'll relax our distance here because 8 plus 6 is 14. That's better than infinity. So we can go A, C, B, D, Z. 8 and 6 is 14. Now we found a path to node Z, but we don't know if it's the shortest path. Right? All we know is there's a path going from A to Z. So we have to keep iterating. So we're going to visit a node. What's the closest node that we haven't visited? There's a 10 and a 14. Looks like a 10. So we'll circle E. And now we relax the nodes that are adjacent to E. And there's only one node, which is Z here. So distance here was 10 plus 3 is 13. That's better than 14. So we'll change this path to say, let's get to node E. A, C, B, D, E, and then go to Z, and that's a distance of 13. And that's the only edge connected here that doesn't go to a node we visited. And now we go back and we try to visit a node. Well, the only node we haven't visited yet is Z, so we'll circle that. And once we circle a node we're after, we can stop. But if we want to find the shortest path to all points, we just do this until all of our nodes are circled. And there's the shortest path from A to Z. And the path turns out to be start at A, come down here, go up there to B, and then go across to D, and then come down to E, and then go over to Z. Alright, that's Dijkstra's algorithm. So questions about that? You may end up watching this part of the video more than once.
So realistically, we're just pretty much going from the starting point and basically going, or like eliminating like path A to B because that's 4 and path A to C is 2. So obviously that would be a better path going that direction. Or
once we've circled C, we know that we've got a shortest path, which is going to be A to C. But it's possible that, you know, A to C is going to look better than A to B, but
Mm-hmm.
we could have something like this. I'm pretty terrible at coming up with these on the fly. But let's see. It doesn't always have to be Z at the end, but you know. So if we had something like this, right, we'd start off from A, and these are all, you know, infinity to begin with. Um, and so, you know, we'll say, okay, the shortest, relax the distances from here, so this could be a distance of 2, and this could be a distance of 4. And then let's visit the closest node, which will be this one, and relax the distances, and this will be a distance of 10, so ACE would be 12. And then visit the closest node now, which would be B, that's 4 versus 12. And relax your distances, and this will become A, B, D for 5. And this is going to end up being part of our final shortest path to Z. Right? We'll visit this next. This will become A, B, D, Z for a distance of, oh, I didn't put distances here, for a distance of 8. And then we relax from there, and I don't know, let's make this 4, right? So we visit this node next. And then the only adjacent node is this one. 8 plus 4 is 12. That's no better than 12. We wouldn't actually relax this one. We'd end up with the same path length. So there's no nodes to relax. So we mark that one as visited. So even though we started off, you know, down here as a preferable node, and we found this was the shortest path to C, we get a much shorter path if we take this more expensive path in the beginning, because the rest of the path is smaller. This 10 really makes this suboptimal. And so we can get here for 8.
I missed a very crucial point in the first demonstration. That was to visit the next closest path.
Ah, okay, yeah. So
obviously make it, you know, more of like an algorithm type thing. Yeah.
Right.
Okay.
It seems like you would have, like in programming, if you were to make this, you would want to avoid edges that possibly bring you back to the same spot, because you'd need to loop over that a bunch of times.
Yeah, so if you're trying to code this, right, you need to store your graph somehow. And you can do that, you know, with an adjacency matrix, or a bunch of lists, you know, that show what's connected to each node and so on. But you need some additional information, right? You need to know the tentative distance to each node. You probably want to know the path that got you that tentative distance, if you're interested in, you know, not just the number length of the shortest path, but the actual path itself. And you also need to keep some kind of flag that says, have I already visited this node? So that when you're relaxing, right, you find all the vertices connected to this one. Here's a vertex, you check that flag, and if it's marked as already visited, it means you've circled this, you don't bother relaxing. And then when you try to find the next node to visit, you only check among the nodes you haven't visited yet. So you might search through, you know, a sequential list of nodes, but if it's been circled, you don't consider that one. And so you find the shortest distance of the unvisited nodes. And there's some cool data structures we'll talk about in winter time that go into implementing this. There's linked lists, there's priority queues, there's all sorts of neat structures that speed this up and make it pretty easy to get a solution out quickly. By the way, this is another example of a greedy algorithm. It's an algorithm that tries to solve the problem as much as possible at each step. And so, you know, it finds the closest node from A and it says, okay, I've solved my problem that far. What do I do next? Well, let's relax distances, find the closest node. Okay, I've solved my problem up to this point. And it's never going to go back and change the path to this node or the path to this node once that node has been visited. So it constantly like tries to eat away at the problem, and as it does, it gets closer and closer to the solution. That's a greedy algorithm. Gets as much as it can as soon as possible. Not all algorithms work well with greedy approaches. And again, in winter, we'll look at a number of problems like a knapsack problem or an egg drop problem that don't work with a greedy approach, and we'll have to do other things. All right, so that's Dijkstra's algorithm. There's a homework question. You can try with that now, and looks remarkably similar to what we just did. But same idea. Start from A, try to get to F. So visit node A, write a distance of 0. These nodes have distances of infinity. First step's going to be, relax the distances. You can get to B for 2. You can get to C for 3. And the path here would be AB. The path here would be AC. When you're doing this problem, though, right, you can do it like I did on here, crossing things out and so on and so forth. But when you're writing this up for credit, redraw the graph after each change you make to it, right? So that you end up with a series of graphs showing what happened here. In other words, when I decided to relax these distances to 2 and 3 or 4, right, and 2, that's a good place to redraw your graph, right, before you make another change. So like if I made this AB and I crossed it out and changed it to ACB, I don't know when those things happened relative to when this became a 10 and this became an 8. So usually once at the end of each iteration, you want to redraw your graph. And yeah, it takes a little bit of drawing. If I do this on a test, I usually give you a couple of pages with multiple copies of this, and then you can just, fill in your numbers along the way. What is the computational expense of this? It's surprisingly efficient. At most, you're going to visit n nodes if you have n vertices in your graph. All right, because each time that you go through here, you visit another node, and once you visit that node, you're done with it. And so there's going to be n iterations of this main two-step loop. But at each point, to relax adjacent nodes is order however many, whatever the degree of your node is, however many edges you have coming out of it. And then to find the new node to visit is potentially in order n. And so it ends up being, a big polynomial time. But it's not too bad. And like I say, you see this in a lot of game code, where you're trying to chase a player or navigate a car down a city street and do it in a way that's as efficient as possible, right? You can build a graph that represents the roadways and then use Dijkstra's algorithm based on where you are, where you're trying to get to, figure out which way to go. So it's pretty fun stuff. All right. Any other questions on graph stuff? And we'll talk a lot about particular types of graphs in 222. We'll talk about binary trees or non-binary trees, which are mostly just like graphs without loops, and a few other properties. So we'll get more exposure to this. All right, well, let's go into our last unit then, which is languages and grammars. And this covers a lot of different areas of computation. We're going to start by looking at languages and what constitutes a language and how can we tell when something is a valid piece of a language and so on. And it's going to lead us into some theories of computation. It's going to lead us into state machines and into Turing machines and ultimately into questions of computability and famous problems like PNP. And we got to do all this in the next like 3.5 lectures. So I'm not going to give you I'm going to give you a homework set for this. I'm not going to grade a homework set for this, right? Because I'll post homework today or tomorrow, but we wouldn't have a chance to talk about it until Monday, and we're not going to get through most of the material until Monday. So I'm going to give you a homework, but I'm not going to grade it. You can submit it, you can ask questions about it, and I can look at it and give you feedback on it. But it's kind of a freebie homework. But this stuff is fair game for the exam. So we want to make sure we understand this material, so the homework will help you do that. All right, so the first topic is syntax versus semantics. Syntax is talking about structure. It's how a collection of symbols has been put together, and we can ask whether that is a valid way that these symbols have been put together. And so Noam Chomsky studied languages and grammars, and I remember one of his examples was something like, the sleeping, colorless, green gas sang silently. And structurally, syntactically, this is a completely valid sentence, right? There's a subject, there's a verb, there's modifiers on this noun, right? So adjectives. There's an adverb that modifies the verb. There's a introductory word, right? This is a perfectly valid sentence. You could diagram this, and it comes out correct. But semantically, meaning-wise, this is kind of ridiculous, right? Gases don't sleep. Gases don't sing. If you sing, you're probably not singing silently. It can't be green and also colorless, right? So this is nonsense. So the meaning is bogus, but the structure is perfectly correct. And in programming languages, if you write a C program and you have a statement like this, right? Is this a valid C program? Will these 3 lines of C code compile? Absolutely. I equals 0. If I equals I plus 1, I equals 0, else I equals 0. But meaning-wise, this is kind of ridiculous, because this is just saying I equals 0. Or I could do this, I could set I equal to 1, and I could say, if this is true, set I equal to 0, else set I equal to 1. Well, it's just going to leave I equal to 1, because this is a silly statement. I is never going to be equal to I plus 1. But syntactically, this is perfect, and the C compiler will say, yep, that's good, and it'll build a executable program from this. So syntax and semantics, totally different subjects. We're not going to deal with semantics. We're not dealing with the meaning of sentences. We're just looking at the structure. And so this brings in the idea of formal languages, of which English is a horrible example, by the way. But a formal language is something like, the C language. The C language is rigidly defined. You can find an exact specification of what constitutes a C program. And so, yeah, so when you get a syntax error, it's literally saying the syntax, the structure of what you've written is not correct. So let me show you an example of a formal language. English is not rigidly defined much of the time. All right, so let's say a sentence is equal to a noun phrase plus, I'm going to say plus to say, you know, followed by a verb phrase. A noun phrase is defined to be an article followed by an adjective followed by a noun, or it could be an article followed by a noun. And a verb phrase is going to be a verb followed by an adverb, or it's just going to be a verb. An article is a or the. An adjective is going to be large or hungry. And you know, this is the problem with English. I'm using or as an operator here, but you know, or could also be, you know, some other part of speech. All right, a noun is going to be a rabbit or a teacher. And a verb is going to be hops or talks. And an adverb is going to be quickly or wildly. All right, so here's a definition of a subset of language. Yeah, I know it's an article because it's in my notes. That's the only reason I know it. I learned like English finally when I started teaching 215. So this is a language. It's not, you know, the English language. It doesn't let us say most sentences, but we have a formal description of a very simple language. And one thing we can do with this description is we can build sentences. Well, how do we build a sentence? Well, we take a noun phrase and a verb phrase and we put them together. How do we build a verb phrase? Well, let's take a verb and an adverb. Okay, what's a verb? Well, a verb is let's say hops. And an adverb would be quickly. So hops quickly, that's a verb, plus an adverb, that's a verb phrase. And if we put a noun phrase in front of that, we should get a sentence. Well, what's a noun phrase? It's an article, so let's say the, followed by a noun. Well, a noun could be teacher. Well, there's a sentence. The teacher hops quickly. So we can use this formal description of a language to construct sentences. Right? Anybody ever play Mad Libs? This is what Mad Libs is. You're basically given a set of sentences that are partially built, and you have to fill in some of these primitives. So it's like, you know, think of a noun, think of an adjective, and then you read the whole story at the end and it's something funny. Right? So that's one thing we can do with these. We can build sentences. And we can diagram this process of building this by drawing something like a tree. We can say we started with a sentence, and that meant we were going to make a noun phrase followed by a verb phrase, and our noun phrase was going to be an article followed by a noun, and our verb phrase was going to be a verb followed by an adverb, article was the, and the noun was teacher, and the verb was hops, and the adverb was quickly. So starting with a sentence, we were able to follow this language and break this sentence down into pieces, break those pieces into other pieces, and so on until we got down to, you know, just words. And then by putting those words in here, we got a sentence. We can do this in the other direction, though. We can start with a sentence like this, with a collection of symbols like this, and say, is it a sentence? So I don't know how many people here have diagrammed sentences in school, but that's basically what you're doing. You would start with something like this, and you'd say, oh, this is an article, and this is a noun, and this is a verb, and this is an adverb, and this is a noun phrase, and this is a verb phrase, and this is a sentence. All right, so those are things that in some ways we're familiar with from school. So let's formalize this. Let's get this into a form that we can do some precision with, so that we can, you know, eventually, not in this class, but in some other class, teach a computer how to do some of these things. So as usual, we need some definitions. And hey, I got curtains now, so when the sun comes in, like it's doing now, I think I can do good stuff. Hey. All right. Vocabulary V, we're going to go back to some set theory here, is a finite, non-empty set of symbols We're going to define a sentence. Sometimes it's called a word, but we'll define a sentence or a word over V is a finite length string of elements of V. Alright, V's a vocabulary. It's a finite, non-empty set of symbols. Think of it as letters, maybe. Think of it as words, maybe. But symbols. A sentence over V is just a finite length string of those elements. Some or all of them, could be multiples. Might not have some of them in. Alright, there's a special string called lambda. That's the empty string. It's a string of length 0. So by a string, just think in C, right? It's a collection of these things just laid out side by side in some particular order. So if we have a string which is comprised of 0 elements from the vocabulary, right? A string that contains nothing, that's called the empty string. We use lambda for that. And that's a really useful string to work with. So we give it a special symbol. It's not the same as the empty set, right? These are strings. These are collections of symbols in a particular order. Nothing to do with sets per se. But the vocabulary, that's a set of symbols. All right. V star equals the set of all sentences over V, or all words over V. By the way, if you're in 224, we just talked about regular expressions and we saw the asterisk. That's the same asterisk. Regular expressions and languages are close relatives to one another. Alright, so V star is a set comprised of all words or all sentences over V. And so to define a language, we can define a language over V. And this is just a subset of V star. And this is what we want to study. So we're studying languages which are subsets of V star, which are subsets of all sentences over V. In other words, particular sentences. So in the case of English, right, we might think of a vocabulary as being a set of words. And then a sentence would be just a collection of words strung out side by side. V star would be the set of all such sentences, every possible arrangement of words, right, as long as the number of words is finite, right, because a sentence is a finite length string. And so, you know, just take any words and slap them on the refrigerator with you know, word magnets, and you've got sentences, right? So the language would be the collection of those sentences that we consider valid, for example. Or if you want to think of this in terms of words and letters, right, our vocabulary could be a set of letters, A through Z. A word, right, would be a finite length string of letters. V star is the set of all finite length strings of letters. So, you know, anything that you can write by just writing down the letters in some particular order. But then the language would be some subset of those. And it might be, for example, the subset that constitutes words you would find in the dictionary. So this is a general description of a language. And so the big question is, how do we specify a language? How do we say what the subset of all possible sentences are that constitute our language? And if this is, you know, the English language, there's one answer. If this is the French language, there's a different answer. If this is Mandarin, right, our set of symbols is going to be different to begin with. But there's still, you know, some subset of all the strings of finite length that are collections of those symbols that constitute, you know, the language that we would call Mandarin. So how do we specify a language? And there's a few ways to do this. So one approach is to list all words. A language is a subset of all of these possible sentences or words. We could simply just make a big list of all the things that are part of the language. And in fact, we do this in English. It's called a dictionary. You can, you know, open up Webster's dictionary, and it's just a big list of words that are valid in this language. And so you see dog and cat and Prometheus, and you don't see, you know, blah blah blah. Maybe you do. Right, so that's one approach, is to list all words. Works great for English. Does not work well for a C compiler. Right, if a C compiler took this approach, it would basically have to have, you know, a database containing every valid C program. Every program that is syntactically correct. And then it could take the program that you're feeding to GCC and say, hey, is this one of these valid programs? That's not going to work really well, right? Most of our words in English don't get up to be 100 characters, but, you know, in C there's no expected maximum length of a program, and so the number of programs would be huge. So that's not going to work really well. The second idea would be list rules for a word to be part of the language. And this is a little more doable. We do this in English too, right? If you have a Q, it's followed by a U. If you have an I and an E, they go in a certain order, except for certain exceptions, right? But those don't always work very well. But there's some rules that we could use to know if something is part of the language of valid C programs, right? Do we have matching curly braces left and right? Do we have matching parentheses? The approach we're going to take is to describe what's called a grammar. So describe a grammar for the language. And a grammar is basically two things. It's symbols and it's rules for producing words. Alright, so we're going to study these grammars. We're going to study ways that we can have symbols and rules for producing words to describe what's part of a language. And we're going to work with one particular type of grammar. This is called a phrase structure grammar. So this is a four tuple. So it's four things which we call V, T, S, and P. Alright, V is a vocabulary. T is a set of what we call terminal symbols. We'll get into some examples shortly, and this will make more sense. The terminal symbols, the set of terminal symbols, this is a subset of V. S is a start symbol, which is an element of V. And P is a set of what we call production rules. And they basically will take the form, something gets changed into something, something old gets changed into something new. And with this kind of quirky looking setup, we can define languages. So let's just do some examples now. So let's make a grammar VTSP. Okay, our vocabulary is going to consist of the following symbols: little a, little b, big A, big B, and little s. Our terminal symbols will just be little a, little b. So it's some subset of our vocabulary. Our start symbol is just going to be this symbol S from our vocabulary. And usually the interesting part of these are the production rules. So here's the production rules for this grammar. So I have a rule which says S can be changed into big A, big B, little a. It says big A can be changed into two big B's. It says big B can be changed into little a, little b, and big A, big B can be changed into a little b. Alright, there's a grammar for some language. And we can ask, what's this language look like? What are some words over this language? Alright, so here's the setup, right? We start with the start symbol, and then we can apply any production rules that we want to change that start symbol into something else. And we can take that something else that we get, and if we can apply further production rules to part of it, we can do that. And your goal is to end up with a word consisting only of terminal symbols. And when you do that, then you've found a word over the language. So for example, my start symbol is little s, and I know that little s can be changed to big A, big B, little a. And I know that AB can be changed to just a little b. And so BA is one string that's recognized by this grammar. Right? My start symbol got to ABA, my AB changed into a little b, so there's my little b and there's my A. I could also take my start symbol, go down to AB, little a. I could take A and change it to two B's. So now I have BB, BA. And each B can be changed to a little AB, so this could go to AB, 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 A. So there's another string recognized by this language. And it turns out those are going to be the only two strings that are part of this language. And you can convince yourself of that by trying different ways to start from S and apply these production rules, and there's really not a whole lot of choices, right? It's deliberately a pretty restricted language. But that's the basic setup. And we'll do this a lot with binary numbers. We'll have terminal symbols of ones and zeros and production rules, and we'll see ways to, construct strings that have certain properties as binary strings and so on and so forth. But this is the sort of intuitive, touchy-feely version of how we use these grammars. Start with the start symbol, just keep applying production rules. Anytime you find a string that's just comprised of terminal symbols, that's part of your language. Okay, not a really good way to describe English. Probably not possible except in some reductionist way. But it works really well for computers. All right, so let me formalize this. And this is just, because it's a discrete structure class and we like writing Greek letters and such. So keep in mind that sort of intuitive version of what's going on, but here's how we would make this more formally using some of the machinery we've developed. So suppose W0 equals, some left piece followed by some Z0 followed by some right piece. So W0 is a string, right? It's got something on the left, it's got something in the middle, something on the right. L, Z0, and R are all also strings. And suppose W1 is equal to the same left piece, but a different middle piece, and the same right piece. Alright, so these are strings. If we can find, some part in the beginning and at the end they're the same between the two strings, and then some middle part that's different, call that middle part Z0 and Z1. Okay, if the following rule, Z0 changes into Z1, if that's part of your production rules, if that's in your set P, then we say the following. We say W1 is directly derivable from W0. In other words, if we had this word in our language, and we had a production rule which says Z0 can change into Z1, then we could take this word and change it into this word, which is W1. So in our grammar, right, W1 is directly derivable from W0 because there's a single production rule that will turn this word into that word. And we have a notation for that. W0 double arrow W1. Nothing to do with propositional logic here. But it says W0 can be changed into W1. So these are definitions. All right. If we have the following situation, if W0 lets us directly derive W1, which lets us directly derive W2, which lets us directly derive, etc., and eventually lets us directly derive Wn, then we can say Wn is derivable from W0. Not directly derivable, but derivable. We can start from W0, apply a series of production rules, and eventually get to Wn. And we have a different symbol for that. We have W0, double arrow, Wn, but we put a little star on the top of that double arrow. And this is called a derivation. So to say this word is derivable from W0 means that there is a derivation, a sequence of directly derivable strings starting from W0 that ends with Wn. So we can start from W0 and apply a series of production rules and eventually get to Wn. That's all that that's saying. All right, so here's our grand definition. So the language generated by G, and remember G is our grammar, so it's this four tuple of vocabulary, terminal symbols, start symbol, and production rules. So this is a grammar, it generates a language. The language generated by G, which we just write as L of G, equals the set of all strings of terminal symbols which are derivable from S. Alright, so all collections of terminal symbols in the form of a string that can be derived from the start symbol. That's exactly the same thing as saying start with a start symbol, apply production rules until you get to a string just made up of terminal symbols. Right, but we can also write this even more formally. L of G is the set of all words contained in T star right? Remember, T star is the set of all sentences over whatever T is. So all the finite length strings of terminal symbols. So it's all the things in this set T star, all the finite length strings of terminal symbols, such that there's a derivation from S to W. Alright, so everything we've done for the last half hour is really just this. The language generated by the grammar G is just the set of all words, all strings of finite length of terminal symbols, such that that symbol can be derived from the start symbol. All right, if you're still with me, send me an attendance ping, please. And let's do a couple of more examples. All right, so let's do a vocabulary equals a start symbol, a 0, and a 1. Our terminal symbols are just 0, 1. So we're going to be making binary strings. Our start symbol is just S. And our production rules are the following. S goes to 1, 1S, or S goes to 0. And we want to find what the language looks like. So understanding that we've gone through this pretty quickly, and this is probably new, but just thinking if we start from the start symbol and we apply production rules, can we get a string comprised of 1s and 0s? Can you think of a string that we can derive from the start symbol?
Zero.
0, right? Because we have a production rule which says S can be changed into a 0. So this is definitely one of the words in our language. It's just plain old 0. All right, can we find a second word?
110.
110, because our start symbol could change to 1, 1S, and then that S could change into a 0. How about one more?
1111S or 11110.
Yeah. Because our S could change into a 11S, and this S could change into a 11S, and this S could change into a 0. So we got 11110. And we can keep doing that, right? So this is, you know, an even number of 1s followed by a single 0. And so this is an infinite language, right? There are an infinite number of words that comprise this language. Each word has finite length, but there's no limit on how large a word could be. I could have 1,000,000 1s followed by a 0. That's going to be recognized by this grammar. So would this potentially mean a numbering system could be a formal language? That would be interesting. So we can definitely make a formal language to represent, say, real numbers or integers or things like that. But I'm wondering if maybe there is something deeper we could do with that. Like actually define a numbering system. And I think that's an interesting question. I don't have a quick answer for it though. Yeah, right? So we're going to do two things with grammars. The first thing, which we've already started, is analysis. We're going to, you know, describe a grammar like this, and then analyze it and say, what are some of the words in this language? And that's a more straightforward challenge than the second task, which is synthesis. Synthesis is where we say, hey, I want a language which contains these words. How do I write a grammar to describe that? And that's going to be a trickier problem. But we're going to do a bunch of examples on the analysis side, and that will give us some practice with working with this setup, these idea of production rules and start symbols and so on. And once we get enough practice with that, then we'll start playing around with some synthesis and say, okay, let's make a language that represents, you know, a string containing an even number of zeros followed by an odd number of ones, right? Can we make a grammar for that? Well, we can. And this is, you know, the physics problem, right? Analysis is, you know, here's a solution to a problem, you know, does it make sense? Synthesis is, you know, here's a problem, come up with a solution now. The synthesis side is always trickier, but the more we do the analysis side, the more our brain gets wired to do the synthesis side. So Monday we'll play around with both of those a fair amount, and then we'll start looking at some other ways to describe syntax, including a way called Bacchus-Naur form, BNF. This is an older way that programming languages were sometimes specified, and there's tools to work with BNF. No, we do not have class Wednesday, so Clark is closed for classes on Wednesday, so just Monday and Tuesday this week. So we'll look at BNFs, and that will take us into a discussion of state machines. I will not use any flip-flops, so don't worry about that, but we'll talk about state machines like 250 state machines. And that will lead us into a particular type of state machine called a Turing machine. And we'll spend a while, probably Wednesday, talking about Turing machines, and try to get to some of the good stuff with incompleteness theorems and halting problems and P versus NP. And we'll try to finish all that up on Wednesday so that Friday we can do review for the final. And then we're done. So good stuff coming up. Take what you can from this. I'll post some homework questions, like I say, ungraded, but you can work on them. We can talk about them. Otherwise, if I don't see you in class tomorrow, have a fantastic week. Have a good break, and I will see you next time.
Bye.
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 See you then.
Have a good break.
Thanks, you too.
Alright, I guess I'll see you tomorrow.
Yeah, yeah.
Okay.
All right, see ya.